Hi students, welcome to exercise 13's lesson on reciprocal quotient and Pythagorean identities. The key word here today is identities. Let's kind of explore what that is. An equation is something like sine theta equals 1/2. There's an answer for that solution. For example, in the first revolution, it's pi over 6 and 5 pi over 6. So that's the value you would put in for theta. And notice that all coterminal angles would also be correct here. An identity is something that's true for all values, or at least almost all. We're going to explore that today. So for example, tan x is equal to sine x over cos x. That's one of the identities we learned earlier. So this is something that's true for any value of x. So any value for the angle you plug in there, that will be true again, mostly. Alright, so recall the following identities. We kind of learned some already coming from the reciprocal trig functions. So, here tan x equals sine x over cos, we knew that one. Cosecant x is 1 over sine, secant x is 1 over cos, cotan x is cos over sine, and cotan is 1 over tan. Alright, so let's first look at the non-permissible values. So the values where this wouldn't be true would be any time the denominator equals to 0. Because if you divide by 0, you cannot do that, right? So that's the non-permissible values of these identities. So determine the non-permissible values of the following identities. What you're going to do is when you're going to do this, is you're going to basically change everything to sine over cos, or cos over sine, or anything in terms of sine and cos. So cotan, for example in this one, cotan is cos x over sine x. Okay? And here on the right hand side, this is 1 over sine x over cos x. Okay, well any value that makes a denominator equal 0 will have issues. So right here, sine x cannot equal 0 from this side. So sine x cannot equal to 0 because you'd be dividing by 0. And over here, notice that either sine x or cos x cannot be 0 because it would create this denominator equal to 0. So on this side, sine x cannot equal to 0. So that's basically the same one as this one, right? So that's nothing different. And cos x equals 0. Okay, well, where is sine x equal to 0? Sine x is equal to 0 at, if you think about here, I'm going to draw a little diagram here. Sine is equal to 0 here and here. So x would could not equal to 0, pi, 2 pi, and that could continue. So let's for now stay only between 0 and 2 pi, just to be a little bit more precise. Okay, so that would be the answers within the first revolution. So sine x cannot equal 0. Okay, we've already answered that here, so we don't have to repeat ourselves. Cos x cannot equal to 0. Well, that would be the other two, right? That would be cos or x equals 0 on those 2 points. So x could not equal to pi over 2 and 3 pi over 2. So these would be the non-permissible values of this identity on this interval here. Okay, over here, so I'm going to change everything to sine over cos. We can leave tan here by itself, and we'll see why in a second. So on the numerator, you have cos x over sine x. That's the definition of cotan. On the denominator, you have tan x minus 1 and sine x. Okay, so what are we going to have? Sine x cannot equal to 0. That's the denominator of your numerator, and it's also the denominator here. So sine x cannot equal to 0. We've actually already solved that. That's over here, right? So we'll repeat that answer. We have another one though, if you look closely, because here, if tan x minus 1 cannot equal to 0. Sorry, tan x minus 1, not equals. So minus 1 cannot equal to 0, which means tan x cannot equal to 1. Right? So I solved, I brought the negative 1 over there. So you have two solutions here, which would give you equal to 0. Let's solve the first one first. So x cannot equal to 0, pi, and 2 pi. Again, that's according to the interval that I gave here. And the second one, where is tan equal to to 1. I hope you guys can think of the spots. It's just simply pi over 4 and 5 pi over 4. And that would be the non-permissible values of tan. Alright? Okay, often, to simplify expressions, we use some of the identities that we know. Often the case is we're going to change everything to sine and cos and try to cancel some things out. So for the first example, let's change tan into sine theta over cos theta. That's just the tan value. And then we're multiplying this, that's a multiply, by cos theta. And all that is over 1 over cos theta, which is secant, right? So that's secant, and that's tan. And then multiplied by cotan, which is cos over sine. Okay, well that works out pretty well. If you notice carefully, I could actually put this on a fraction over 1 as well. Let's just look at the numerator start. Notice that we can cancel out the cos theta. And here we can also cancel out cos theta. So what would we have left? We would have sine theta over 1. So I'll just write sine theta left on the numerator. And on the denominator, I have 1 over sine. Okay, well, I can bring this over here. So, anytime you have a fraction or a number divided by a fraction, I recommend you guys write it like this. You'd have sine theta divided by 1 over sine theta. And this is going back to, I don't know, grade 7 math. Whenever you're dividing by a fraction, right, what you're going to do is you're going to change that sign to a multiplication, and you're going to flip that fraction. So you have sine theta times sine theta, which means you have sine squared theta. That is our simplified expression of this. Okay, so same thing again. So I'll see if I can stay within the constraints of that question this time. Okay, so I'm going to start right here. So cot x, that's cos x over sine x, that's your numerator, divided by 1 over sine x, and here is just cos x. Okay, so there's nothing really I can simplify here, and there's nothing I can simplify here, but I can put this onto one fraction instead of multiplying. So I'm going to have cos x over sine on the numerator, divided by cos x over sine x on the denominator. Well, notice that the numerator here and the denominator are equal. They're the exact same. Therefore, this is equal to 1 when you're all simplified out. Alright, last one. Over here, move this over a bit so I can write the first step. I think I'm going to be able to stay within my lines this time. Alright, so up here we have 1 over cos squared theta. Don't forget, if it's secant, it's 1 over cos. And then we multiply that by cos theta. And all that's divided by 1 over sine theta. Okay, so just quickly we can see on the numerator, we can simplify this cos and this cos over here, so this square is gone, and it'll cancel out this cos. So what we have left on the numerator is 1 over cos theta divided by 1 over sine theta. Okay, so as I mentioned earlier, try to write this as, I'm going to write on the open space here a little bit. We're going to write 1 over cos theta divided by 1 over sine theta, which is going to be 1 over cos theta times sine theta over 1, and which means you have sine theta over cos theta, which is the definition or the identity of tan. So sorry it went a little long, but this expression over here is equal to this expression over here. Okay, next question. Verify that the equation given here is true for x equals 3 pi over 4. So all we're doing is proving that this is equal to this for any value of x, but more specifically, in this case, 3 pi over 4. So let's start with the left-hand side. So I'm going to say left-hand side. I'm going to plug in 3 pi over 4. So you're going to have secant of 3 pi over 4 divided by tan of 3 pi over 4 plus cotan of 3 pi over 4. Okay, well, secant of 3 pi over 4, Okay, so you got to look on your unit circle, find the value of cos, and then, inverse it, right? So this is going to be negative 2 over square root of 2. Okay, on the denominator, tan of 3 pi over 4, well that's negative 1, because x and y have the same value, and cotan is actually also going to be equal to negative 1. Okay, so I'll flip over here. So what we have is negative 2 over square root of 2 divided all by 2. Sorry, negative 2. And we're going to, anytime you have a fraction and you're not sure what to do, I'll help you out. So this is divided by negative 2, which means it's negative 2 square root of 2 times negative 1 over 2. Again, the negative doesn't matter where you put it. And those two cancel out. Two negatives, which means I have 1 over square root of 2. That's my left-hand side. Now for the right-hand side, we just have sine of 3 pi over 4. Well, that's simply negative square root 2 over 2. Sorry, not negative, because we're in the second quadrant. And we haven't really proven that they're equal yet, but remember, if I have a rational in the denominator, I can just rationalize the denominator by multiplying by the square root of whatever number that is. So 1 times square root of 2 is square root of 2, and square root of 2 times square root of 2 is 2. So we've proven that the left-hand side and the right-hand side are equal. Last part I want to do for this question, all I want to do is verify that, or find the non-permissible values of this expression. Okay, so here, for the numerator, I'm just going to write the right-hand side here, first of all, does not have any non-permissible values. There's nothing on the denominator. So I'm going to rewrite the left-hand side as 1 over cos x. So we're going to have a non-permissible value here, right, because you can't divide it by 0. And over here, we're going to have sine x over cos x and plus cos x over sine x. Okay, so the obvious ones are cos and sine cannot be 0. All right, cos x cannot be 0, sine x cannot be 0. Okay, now there's one more thing. However, if you look at the denominator, I'm going to go back to that original over here. Oops, I'm going to draw there. We also have to say that tan x plus cotan x cannot equal to 0. So the sum of the two cannot equal to 0, which basically means that tan x cannot equal to negative cotan x. Okay, so that's actually can be quite complicated. However, we're lucky, and we can discuss this in class if you guys want, but this actually does not happen because tan and cot always have the same sign. So for any angle, tan and cot will have the same sign, therefore they will not be equal to each other. So this doesn't happen. The only two we have to worry about is those two over here. So cos x cannot equal to 0 and x pi over 2 and 3 pi over 2. And also sine cannot equal to 0 at 0 and pi. Notice that I didn't include 2 pi this time because 2 pi was not included in our solution. So these would be our non-permissible values. Okay, next we're going to kind of explore Pythagorean identities. They come from what we talked about in class, sine theta equals y and cos theta equals x. So if we started with x squared plus y squared equals 1, which is anything on the unit circle, I can replace x with cos, and I can replace y with sine. So sorry, I flipped those around. No big deal. Okay, so I replace y with sine, x with cos, and I come up with this trig identity. This is a very important identity we're going to see very often. And all these identities coming from that are based on this idea. Okay, so if I took equation number 1, and I was to divide everything by cos, so I'd divide sine by cos over here, divide cos by cos, divide 1 by cos, it would produce this identity. So sine squared over cos squared is tan squared, cos squared over cos squared is 1, and 1 over cos squared is secant squared. I could also do the same thing by dividing by sine. So I take this formula over here, and I divide everything by sine squared. So you'd have this, this, and this. This is 1. This is the definition of cotan squared, and this is 1 over cosecant. Sorry, this is 1 over sine, which is cosecant squared. Okay, and I can now take these three formulas. So for example, I take this first one over here, and I can manipulate it so that way it's not just sine squared plus cos squared equals 1. So I could bring the sine over, so it becomes, so let's come back over here. I bring that sine over, I have cos squared equals to 1 minus sine. Or I keep the sine here, and I move the cos over, and I have 1 minus cos squared. So that's the same thing for all of these. So technically you have 9. Notice that these are the only 3 that show up in your formula sheet. You can take a quick look. But these are just manipulated from those 3 original ones. Okay? So note that these trig identities are only true when these functions are squared. For example, cos or sine plus cos is not equal to 1. That would be like saying x plus y is equal to 1. And that's not necessarily the case. It does happen, but it's very rare in that unit circle. Okay? So make sure that these are squared. That's why they're Pythagorean identities. Everything in here is squared. Okay, here the last example. What we're trying to do is we're trying to prove that this side is always going to equal to 1 no matter what. Okay, so first of all, we're going to use this right here as our first Pythagorean identity. So recall the sine squared x plus cos squared x equals to 1. That was the first identity, number 1. Notice that if I was to bring the cos over here, I could replace this with sine squared. So if I was to bring the sine squared over the cos squared over the other side, I'd have, this would be an equals to 1 minus cos squared x. Okay, well that means I could replace this left-hand side, so we're going to work with the left-hand side here. I could replace the first part with sine squared x. Alright, well this part, I know this by 1 over cos. So often in identities, what we're going to do is we're going to change everything to sine and cos, a little bit like what we did in the beginning of this lesson. And then this part, I can change into cos over sine. So cos squared x over sine squared x. Well, notice on the left-hand side, if I look at all the numerators multiplied together and all the denominators multiplied together, there's some things that I can cancel out. This sine squared and this cos squared cancel out, and all I'm left with is 1, which is equal to the right-hand side. So all I've proven here is that this side and this side are equal. The last thing I want to do, find the non-permissible values. So notice that cos squared and sine squared we have on the denominator, which means cos squared x cannot equal to 0. Well, it doesn't matter if it's squared or not, because 0 squared is 0. So really what we're doing is cos x cannot equal 0. We're going to do the same thing for sine squared x cannot equal 0. That means sine x cannot equal to 0. And we're looking for the interval 0 to 2 pi. Therefore, x cannot equal to pi over 2 and 3 pi over 2. And over here, x cannot equal to 0 and pi. So these would be the non-permissible values. So that means this is true for all values of x except for these values on the interval 0 to 2 pi. Alright guys, good luck. I hope this lesson was understood.